In this video, I'm going to be doing a general overview of how to solve exponential equations. First of all, it's important to recognize what an exponential equation is. I have one up here in the upper right corner. Y equals b to the x, where y is your dependent variable or f of x. X is the independent variable, and b is just some number. Greater than 0, not equal to 1, which you should have learned in some previous studies or by watching some other videos. So again, to solve an exponential equation, we need to have an exponential equation, which means that variable that we're hunting for is going to be up in the exponent position. Exponential functions are always increasing or decreasing. If you've learned how to graph these functions, these shapes might look familiar. This is the increasing exponential, and that happens when we have a positive x up here. This is actually the decreasing exponential curve. Sometimes it's called an exponential decay, and that is because we have this negative sign up in front of the variable. Going back and recognizing our transformation rules, and specifically the reflection rule, we would recognize that if you have your parent exponential, here the exponential growth function, if you put a negative sign in front of it, it has the effect of flipping that function, and then you end up with the decay function instead. There are two primary methods for solving exponential equations, and they're rooted in the following things. Number one, exponentials pass the horizontal line test. That means it's a one-to-one function. The other thing, if you've watched previous videos, is remembering that the exponential function and the log function are inverse functions of each other. And what that does is that provides us a secondary method for solving. And so again, there are two primary methods for solving exponential equations. The first is called one-to-one. The second is called the inverse property. Which method should you use? The one-to-one property method is the slickest, most efficient way to solve these. The problem is not all exponential equations are one-to-one. So if your problem is not in the one-to-one format, then you'll go use the inverse property instead. If something is in the one-to-one format and you don't recognize that, you could go use the inverse property. It'll just take you longer. It's a little bit more tedious. Okay, so what I'm going to do in this video is explain what each one of these properties are and do a brief example. And then I have an additional video where I go through more examples in depth for one-to-one, and then another video that goes more examples in depth for the inverse property. Okay, so what are these two methods? The first, the one-to-one property. Basically, if you have something that's one-to-one, you recognize you have a certain pattern. And what that means is we actually can have two exponential expressions, and if the bases match, so again, these are just some number, they're both 2, they're both 10, they're both e, they're both 100. Whatever they are, these match. If that's the case, the exponents that are up here with each term, you get to just pull those out and write an algebraic expression setting those exponents equal to each other. It's very, very powerful, because if this variable, this unknown that we're trying to solve, we will not figure out who that is. If it's stuck up in an exponent, we need to be able to get it down to the main line of an equation. And the one-to-one property is a very powerful tool that allows us to do that. So again, if these bases match, we can take the exponents and simply set them equal to each other. And then that may result in an algebraic equation that we have to go solve to isolate that variable x. I'm going to show you a quick example right here. So this problem may say, solve the following exponential equation. It's definitely an exponential because my variable I'm trying to find, which is the x, is up in an exponent position. A quick glance yields it is one-to-one. We have the same number here, they're both 2. What that means is I can take these two exponents and simply set them equal to each other. So I'm going to write x squared equals 4. So now I have an algebra problem that I should know how to solve. In this case, since x is squared, I'm going to just square root both sides. Square root of x squared equals x equals, and the square root of 4, that is plus or minus 2. And so this would be the solution to that exponential. If I want, I can take the plus and the minus 2 one at a time and put them back into the original problem for x and validate that they are indeed solutions. I don't need to do this from a legality standpoint. If you remember from your studies of exponentials, the domains for exponentials are actually all real numbers, and that's further supported by these graphs up here. X can go all the way from negative infinity to positive infinity in either case. And so when I choose to check these answers, I'm not checking whether they're legal. I'm just checking to make sure that I didn't make an algebra mistake. That is not the case when we get to the counterpart, when we try to solve log equations. We do have domain restrictions in those cases. Okay, well, what if your exponential is not 1-to-1? You don't have this situation. Well, then we need to use the other property instead, and it's called the inverse property. And again, it applies because the exponential equation and the log, they're actually inverse functions of each other. So if you remember from your study of log rules, if you have an exponential written as y equals b to the x, we could choose to rewrite that in its log form instead. A quick refresher, the exponent is written by itself. We write the word log. The base of the exponent becomes the base of the log, and this number over here, or letter, whatever it happens to be, that was by itself, now is embedded as the argument of the log. So again, if I'm trying to solve for x, if it's stuck up in the exponential position, I won't be able to figure out who that is until I get it to the main line. So switching back from exponential into logarithmic form, that allows me to isolate that x. Interestingly enough, there's another way to do this as well, another way to turn an exponential into a log. And how we do that is if we simply take the log of both sides. So if we start out with y equals b to the x, if I don't want to do what I call backwards mapping, like above, I can actually just write the log in front of both expressions. Whatever log I write, it has to be the same. Here you can see I wrote base 10. I could write the natural log, I could write log base 2, log base 3, whichever log I choose to use, it just needs to be identical. But by writing the word log in front of both sides of this equation, I now can utilize that log rule that allows me to take an exponent that's sitting in the argument and pop it down in front of that log expression. And that's another method for getting that x down to the main line where I'll be able to solve for that. And I'll show you a quick example. In this problem, I'm actually going to do it both ways. So if I was given e to the x equals 10 and I was asked to solve for that, again, my x is up in the exponent position, so this is an exponential equation. This is not 1-to-1. E and 10 are not the same. I can't do anything to make them be the same. So I'm going to do this the inverse property, or what I call the long way, by turning it into a log. So first, how about we backwards map it? So if I take an exponential and want to turn it into a log, I'm going to write the word log. This number that was by itself now becomes embedded as the argument of the log. The base of the exponential, which happens to be an e, now becomes the base of the log, and the exponent now is written over here on the other side of the equals sign. And so you can see I've isolated x. So this is actually what x equals. If you do know your log rules, however, you'll remember that the log base e, there's a better way to write that. That's actually called the natural log. And so x is the natural log of 10. If my instructor wanted me to write that as a decimal, I could then go do that in my calculator and present it that way. So let's look at the other method. What if I didn't want to just back map this into its log form? I could choose to take the log of both sides instead. So let's get ready to do that. Which log should I do? You can do any log that you want. However, there are some choices that are better than others. If your base to the exponential is an e, it really is in your best interest to take the natural log of both sides, because we're going to end up with the argument and the base matching, and that will allow for some simplification. So let's do the natural log of both sides. That allows me then to take my exponent, drop it down in front, and so now I have x times the natural log of e equals the natural log of 10. And if you remember from your log rules, the natural log of e, that's actually 1, because if you remember, there is my base. So the argument and the base match, that becomes 1. So I really have x equals the natural log of 10. And so you can see that it doesn't matter which method I use, I will get the same answer. There are some problems I'll show you when I go through the inverse property video that doing the log of both sides is actually a little simpler and easier than back mapping. And a lot of word problems that we end up with, we actually usually take the log of both sides. It ends up being a slick way to do that. But overall, this is your general approach for solving exponential equations. You recognize that you have an exponential, and then you ask yourself, is it 1-to-1? If it is, let's please do it that way. It's the easiest, fastest way. If it's not 1-to-1, then we'll use the inverse property instead, and we're basically going to turn the exponential into a log and solve it that way, and we've got 2 options for doing that. So I hope this was helpful. I will post 2 additional videos that provide several more examples. Some examples of using 1-to-1 and some examples of using the inverse property, and I hope that you find them helpful.